Black holes are regions of space-time in which the gravitational pull is extremely intense. We call them holes because they can be seen as a complement in space-time of the region which is causally connected to infinity, and we call them black because not even light can overcome the gravitational pull, so that nothing escapes out from a black hole. Actually, the second part is not so accurate.
Wait a minute.
One can wonder if they are really black, and there are strong reasons that suggest that indeed black holes must emit some sort of radiation. This was proven by Hawking in the 70s, and to understand his argument, we'll have to go beyond Einstein's theory of general relativity. The relevant observation to understand this is that the laws that govern black hole mechanics are strikingly similar to the standard laws of thermodynamics. To see this, we can write down explicitly the first, second, and zeroth law of thermodynamics for a system, thermodynamical system, of energy E, temperature T, and entropy S, as you can see here. And we can compare these laws to the equations that rule black hole mechanics for a black hole of mass m, area A, and surface gravity kappa, as you can see here. These two sets of equations become identical if we identify the quantities that appear on each side, as you can see on the screen. However, there is some undetermined part, which is the constant multiplying and dividing temperature and entropy. So, this analogy is suggesting that black holes should be understood as thermodynamical systems. However, it is not clear at this point whether this is just an analogy or is some physically meaningful identification.
I'm going to use all the power of my brain.
To understand whether this should be taken seriously or not, one can deduce that black holes actually should have some entropy. Otherwise, if they were non-entropic systems, one could just remove entropy from the universe by throwing something into a black hole. Then the entropy of the object that's been thrown would disappear from the universe, and that is not allowed by the second law of thermodynamics.
In this house, we obey the laws of thermodynamics!
However, there is a main obstruction towards regarding a black hole as a thermodynamical system, and it's the following. So if black holes, as we have seen from Einstein's theory of relativity, do not emit any sort of radiation, then, according to thermodynamics, such an object should have vanishing temperature. Otherwise, it would radiate. However, this is in contradiction with the analogy we have just found, because this analogy tells us that black holes actually, in this identification, should have a non-vanishing temperature. This puzzle was resolved by the famous discovery of Hawking in 1974. He showed that if matter is treated quantum mechanically, then black holes do actually emit some radiation in the form of a black-body spectrum at a very particular temperature. This temperature is known as the Hawking temperature, and it confirms that the previous identification is actually physically meaningful. This is a very important result for two reasons. First, as we've said, it confirms that black holes are genuine thermodynamical systems. And second, it provides precise and definite predictions for the value of the thermodynamical variables associated to a black hole.
Your theory of a donut-shaped universe is intriguing, Homer.
Particularly important is the prediction for the entropy. The entropy of a black hole is given by the Bekenstein-Hawking formula, and it is very important because it refers to the microscopic structure of a black hole. This is one of the main avenues we have nowadays towards understanding quantum gravity.
If you enjoyed the video, like and subscribe. And don't forget, you ask CENTRAnswers.